Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
As you see, this is a joint work with Eric Demaine, Uri, and Mohammad Taqi Hajiaghayi. So let's just start with the definition of the problem. It's very similar to the set cover instance with a minor change. So we have a universe of elements E1 up to En, and we are also given a collection of subsets of this universe S1 up to Sn. And our goal is to find a sub-collection of these sets in order to maximize the number of elements that are covered by these sets exactly once. So we don't want to cover all of them. Maybe it's better to not cover some of them. What we want to maximize is those that appear in exactly one set. So here's an example. I draw these relations as a bipartite graph in a natural way. So here are the sets, and here are the elements. There's an edge if the element belongs to the set. And here's a solution. If we pick these two sets, then these elements are unique covered. This is not considered because it's covered by two sets, and this element is not covered at all. So the size of the answer here is 6, because 6 out of these 8 elements are covered exactly once. Okay, so this is the definition of our unique coverage problem. Now, there are some applications. I name a few of them here. One of them is the wireless networks. In fact, somebody from AT&T brought this problem to our group, and the abstract model for this problem turns out to be this unique coverage problem. So suppose we are given a region for mobile clients, and we are also given a collection of potential base stations. We have to install a base station for transmitters. And each base station will cover a range of a region of area. So here are the circles that will be covered by each base station, potential base station. And we have to select some of these potential candidate places to install the station so as to maximize the service. And what do we mean? A client is going to be serviced if it is within the range of at least one base station, and if it is within the range of several stations, then because of the single interference, the service quality is not very good. So ideally, we would like every client to be serviced by exactly one station. So for example, so we want to maximize the region, or if you consider a discrete model, you want to maximize the number of unit regions that are served by a few, and in the best case, only one station. There is an example. If you pick these base stations, then these are the areas that are covered twice or not covered at all. So these are the bad areas for us. If you
So is there a physical reason as to why covering something twice is bad?
Twice is also okay. So in the next slide, actually, I'm going to say covering a few times is okay, but if it's like 20 stations that can reach one area, then the signal difference will be just too high to give a reasonable service quality.
So can you also formulate a problem where it is where you subtract more if there's more multiple coverage of it?
So in the general case, you can model it. So we say if a client is within range of I stations, then we have a service quality Si, and if S0 is 0, S1 is better than S2, and it declines. And you can usually assume that only the first few values of Si are non-zero, and it grows, then the Si's all become 0. And we can also assume that there is a cost associated with building a particular station in a different location, because maybe it's on the top of a mountain or etc. So they have different costs. And we also have a budget to spend to build all these stations. So considering all these constraints, we want to maximize the total service quality or average service quality per clients, given these costs for building the stations and the budget that we have to spend. There is another application, well, not application, but there's another problem that is somehow related to the problem that we talk about. It's called envy-free pricing. It comes from economy, we would say. So assume that we have a single seller, and the seller has m different products or items to sell, P1 up to PM, and we have a certain quantity of each product. It can be unlimited, but there's also a possibility of having a limited quantity. And there are n buyers, each of which is interested in some subsets of these products, which we call bundles. And each buyer has some valuation for a bundle, and by some means, for example, by previous experiences, the seller knows more or less the price that each buyer is willing to pay for each bundle. And what we are going to do, we want to sell these items. We want to price the items and sell them to the buyers. And a buyer's utility is the difference between the price he or she is paying with the valuation he or she had. So basically you can say how much you save with respect to the price that you had in mind for that bundle. And a buyer is going to buy if the price is less than or equal the valuation. If it is higher than valuation, then the buyer will not buy that bundle. Now the seller has to set the prices for all these items and decide which bundles to sell to whom, so as to maximize his or her own profit and make sure that the pricing is envy-free. And what do we mean by envy-free is that every buyer is sold a bundle that he or she is most interested in. So he or she doesn't want to change to something else. So he's happy with the situation. Now there's a special case, as I said, if we assume that we have unlimited quantity of every item, and we can also assume that every buyer is only interested in one bundle. So he comes to the market, wants to buy a subset of items. If he can buy all of them, buys, otherwise just leaves. And so there's only one bundle, and buys it if the cost or the price is less than or equal to the valuation that has in mind. Now this case, this special case is also APX-hard or maxSNP-hard, and there's a recent approximation algorithm by I don't want to name just one person. I think it's Venkat, Hartline, Karlin, Kempe. I forgot the other K. Kenyon and McSherry. Yeah, in SODA 2005. So they get a logarithmic approximation for this case. And what we are going to show is that unique coverage is a special case of envy-free pricing. And we are going to prove a hardness for unique coverage, and therefore it implies a hardness for envy-free pricing as well. And the reduction is pretty simple. So we reduce it to the special case of unlimited supply, single-minded buyers or users. So for each subset Si that we have, it corresponds to a product, and every element EI is going to correspond to a buyer. And the buyers are going to have valuations 1 for a bundle, and the bundle that they're interested in is defined naturally. It's going to contain the items whose corresponding element is in the set that corresponds to this buyer. And we can assume that all the prices that we are going to set is either 0 or 1, because the buyers have valuation 1. So it's within a constant factor loss in the approximation ratio. We can get to this case by just rounding all the prices up or down. And a buyer will buy the bundle if at most one of the items is priced at 1, because if 2 of the items are priced at 1, then the cost is 2 more than valuation, he or she won't buy it. So if at most one item is priced at 1, they will buy it. And of course, you want to maximize your profit, so you want to make sure that the 0 ones that we have to assign maximize the number of bundles with exactly one item priced at 1. And this is exactly the unique coverage problem. So the profit that we make is the size of the exact cover solution that we have for this particular case.
What does it say about the problem that in the many author paper is considered?
So they give a logarithmic approximation,
Right.
and this is a special case of it. We reduce the unique coverage. We will show this is a reduction from unique coverage, so that a special case is at least as hard as unique coverage, which we will show is sub-logarithmic. It's better than APX-hardness.
Wait, so the special case is hard. So was theirs, what kind of a bound was theirs? Did
So
they have-
for the general case, the best bound was APX-hardness, which also is true for the special case. Now we prove that this special case
is better.
Has a better hardness.
You're right. Okay.
Is it easy to see that the prices we can assume are either 0?
You can round them up or down in a randomized rounding, in a standard randomized rounding, and the calculations are easy, but you will lose a constant factor on the
So
price.
constant factor,
So-
which depends on what?
So by doing this, you only lose a constant factor in the optimal solution to go
Right,
from unique
constant
coverage.
factor that's scaling like what?
2.
Something like 2.
Okay.
It's not huge, no, it's like,
It's not.
I think it's E square or something, but it's
Okay,
a small
whatever,
constant.
whatever, but it's not a ridiculous constant.
Yeah, no, it's a very small constant, definitely less than 10, but.
Okay, good.
So,
Constants are small.
All constants are small.
okay. Now another problem that is somehow related is the MaxCode. So the standard definition of MaxCode, you want to divide graph into 2 sets, S and complement, such that the number of edges running in between is maximized. Now MaxCode is a special case of unique coverage problem. If you consider every neighborhood of vertices as the sets and the elements correspond to the edges, and of course an edge is unique covered if the 2 endpoints belong to 2 different sets. So the size of the unique coverage is exactly the elements, the edges that are running in between. The other edges are either covered twice or none. So we get the same hardness for unique coverage as for MaxCode. Now there are some related problems. So first one is, of course, the standard set cover problem, where you want to minimize the number of sets that cover all the elements. We know the upper bound, which is a simple greedy algorithm, gives by order of log n approximation. And we have this hardness by Uri, which shows that essentially that's the best thing you can do unless NP is a subset of quasi-polytime. Another similar problem is maximum coverage. The input is again same as set cover, but every set this is the budgeted version of maximum coverage. Every set Si has a cost and every element has a weight. And again, we have a total budget. And with this budget, we want to pick some of these sets in order to maximize the number of elements that are covered. Now again, for this problem, a simple greedy algorithm gives actually a constant approximation. And it's not too hard to show that essentially this is the best approximation you can get. Now, when we started looking at unique coverage, we were hoping that a greedy maybe gives you a reasonable approximation algorithm. But unfortunately, any natural greedy algorithm that we tried.
But also for max coverage, greedy doesn't give you it. You have to modify it.
You have to modify it. But it's not terribly hard. I mean, it's
Right,
still
you're
a
saying
greedy.
even the modified version.
Any greedy algorithm that we could think of didn't work for unique coverage. I mean, a particular example that is bad for most of them is just this set, if all the sets have size 2 and have one element in common. So, of course, the answer is to pick all of the sets where this element is not unique covered, but modifications of these are counterexample for any natural greedy algorithm that we could think of. If you consider a parameter that gets better and better as you go, this is a bad example. And one final problem that is related, I'll get back to this at the end, is a classical problem called radio broadcast, which is studied since late 80s. We have a network of processors that communicate in a synchronous manner in rounds. There's one particular node that has a message that needs to be broadcast to all the nodes. And every round, a node that has already received the message can broadcast it either to all of the neighbors that it has, or it can be silent. So either you send it to every neighbor or do nothing. And a vertex receives a message exactly if one of its neighbors is transmitting. For the same reason, if there are several neighbors sending in, then because of signal interference, you don't get the message at all. And the goal is to design a schedule of rounds so that the message is transmitted to all the nodes in minimum number of rounds. And this is called the radio broadcaster schedule. Now, the unique coverage problem, you can think of it as a single round of a greedy algorithm for radio broadcast. So in one single round, some of the nodes are broadcasting, and if you want to maximize the number of nodes that receive the message exactly once, then you're doing a unique coverage. So if you want to try greedy, then in every round you're using unique coverage solutions in your graph. Now, this problem, there's a long line of research, and approximation algorithms have improved until recently. So there's an obvious lower bound of diameter of the graph, because if you're doing in rounds, so you need to have at least d rounds if d is the diameter. But there's an upper bound of d plus log square n randomly and deterministically. You can do it in log cube. And there's also hardness by Elfman and Kurtzos, where they show there's a log n factor hardness. And they also prove an additive log n square hardness. So there's still a gap between upper and lower bound for this problem. So here are the...
There's no complexity necessarily associated with the problem, right? I mean, you could just, no computation. I mean, you could also ask the question, can you actually do it in d plus little o of log squared n randomly with exponential computation time, right?
You can... Oh, this is not... yeah, you're right. But the decision version, this is for the graphs of constant diameter.
Okay.
Can you decide what's the minimum? I come up with a schedule. So here are the results. In terms of approximation algorithm, there's a log n approximation. Even for a more general case, which we have a budget for the total budget to spend, there are costs on the sets and weights on the elements, and you want to maximize the total weight of unique covered elements. And in terms of hardness, which is the main result of this talk, is that assuming that NP problems don't have sub-exponential running time algorithms, then we get sub-logarithmic hardness for unique coverage. Now, this del sigma of epsilon is a very small growing function of epsilon under different complexity assumptions. Sorry, I should have changed this 1 over log, the change of notation. So under different complexity assumption that random instances of free set are hard, on average, we get slightly better hardness of log to the 1/3 roughly. And I should note that the algorithm is simple, and it was actually implicit in the previous works on radio broadcasts by several others that had worked on it. So the main result is just this theorem 2, which is a hardness result. So I'm going to go into some, show you some proofs for the algorithm and as well as hardness.
Okay, so your theorem 1, you're saying, is already implied by the radio.
There's no implicit, I mean, this unique coverage was not stated
They
explicitly.
didn't realize that
there's
it mapped into
yeah.
that from, but once you realize it, then you can take your algorithm.
It doesn't take much time to, you know, so the idea was already there, so we just did some minor,
Okay.
we don't claim. Although there's no, there was no hardness result for, I mean, there's no implicit, as far as we know, explicit this problem that they know. So the approximation algorithm is this. We start with any minimal solution of set cover. So S prime is a set of those sets that cover all the elements, and if you remove anything, any set, then it's not a set cover solution anymore. And we cluster the elements into groups, log m groups, based on this. An element is going to be in group I if it is covered between 2 to the I and 2 to the I plus 1 times. So every element in a group, they are covered roughly about the same number of times. So they are covered, the number of times they are covered differs just by a factor of 2. Now, just focus on the group which has the maximum number of elements and ignore all the other groups. Clearly, that group has at least size n over log n. And what we are going to do is, for every set, so ignore all the sets that have no relation with this group at all. So just focus on this element and the sets that contain them. We are going to do a random experiment. We throw away every set with probability 1 over 2 to the I and keep them, we keep them with probability 1 over 2 to the I. Now, if you look at every element in this group, you see that the expected, so every element is going to be unique covered with constant probability. So the expected fraction of the elements that are going to be unique covered in this group is a constant fraction of the size of that group, which is going to be, the constant is something like 1 over e squared, or even maybe better than that. So we can cover always at least n over log n elements. So the size of the solution is always at least this big. So that's pretty much the algorithm and its proof, more or less. Now, to prove hardness, we are going to use the same idea of clustering elements and using the fact that elements in different groups have different density of coverage.
Where did you use the fact that S prime was minimal?
Sorry?
Did you use the fact that S prime was minimal anywhere?
No, I'm just saying that I throw away irrelevant sets.
I was asking, did you ever use the fact that S prime is the minimal set cover as opposed to just a set cover?
I've taken the whole universe.
Yeah, you could have taken all the sets.
I guess something might be covered
More than 1 times. I see. What is M? Is it the number of elements in the universe or the number of sets?
M is the number of sets that you have. So N is the number of sets, right? I don't think we...
You could, instead of log m, say log s over I.
Yeah. Log S prime, assuming that they are polynomially related. Now, for the hardness, I need to define a different problem, which is this. So assume that we have a bipartite graph. It's balanced, so it has n vertices on A side and B side. Now, we know that finding a bipartite, independent set in a bipartite graph is easy. Now, suppose that we ask, we are also given two parameters, n of A and n of B, and we are asking if there is an independent set such that it has at least size n over A on the A side and n over B on the other side. So we put some restriction. We don't want a very imbalanced bipartite independent set, just picking one part and not the other part. So we have some restriction on the number of elements you can pick vertices from each part. Now, this variation, which is called balanced bipartite independence, that turns out to be a difficult problem. And we are going to use a reduction from this variation to unique coverage. So suppose we have this bipartite graph, and these are these, and we have these parameters gamma, gamma prime, delta, and delta prime. So balanced bipartite independence set with these parameters is to decide.
Wait, I've forgotten already. So what? Oh, you haven't defined it.
No, I'm just defining what is a balanced bipartite independence set. Now I'm defining the problem. The problem is to decide between these two cases, where you have, let me draw the picture, where you have a balanced bipartite independence set with size n to the gamma on the left, and n over some exponent of log on the right. And in the bad case, you don't have even a bipartite independent set of size, these two, n to the gamma prime and n over log delta prime of n. So we want the size on the left be polynomial always, and they're polynomially related. And on the right, it's always a sub-logarithmic fraction of n. So the problem is decide whether you have these large bipartite independent sets or you don't even have those small ones.
Gamma prime.
These are
Less than 1, so actually the ones on the left are smaller, is what you're saying. Or not? Right? Yeah. Okay, the ones on the left are smaller.
Yes. Well, I draw the picture.
Right. No,
there.
I don't care how you.
Yeah.
I was just trying to make
Yeah,
sure that I
on the left
understood.
is actually
So they're
smaller.
both sublinear. So they're both have no density.
Yeah.
I mean, have zero density. But it's
with
just
respect to
by
n.
they have much less than zero density on the left
Yeah.
and a little less. Than
So
zero
what
density.
is important for us is that the difference between these two cases is polynomial. The difference between these two cases is sub-logarithmic. Now, so what is the main theorem?
I see. Delta and delta prime are both less than 1, is it?
Yes.
I see. So it's like n over square root of log n and n over cube root of log n, things like that. Okay.
Well, that's what we could prove. Ideally, if you could prove, it could be, that's for the purpose of our proof to work. Otherwise, I mean, if you, the reduction that we give is general, but the hardness proof that we can get works with this setting of parameters. So here's the main reduction. We reduce balanced bipartite independent set to unique coverage this way. So if you give me this graph G that I just draw in the other page, and those parameters gamma, gamma prime, and delta, delta prime, we construct an instance of unique coverage where the size, the number of elements is n log n, and where was the size of each part of this bipartite graph, and such that if the graph G was a yes instance, in other words, it has large bipartite independent set, then the size of set unique coverage solution is n log to the 1 minus delta of n, and if it is a no instance, then the size of the solution is n log 1 minus delta prime. So they differ by a factor of log to the delta prime minus delta. So that's what the hardness factor we get. So if we could prove a hardness for balanced bipartite independent set where delta prime is 1, for instance, and delta is 0, then we would get a logarithmic hardness. So the main part is just this reduction, and then you have to prove the hardness for.
I see. So you very much would like to have other values of delta.
Yeah.
Yeah.
But it's the thing, the techniques
Sure.
we have.
No, it's nice already, but.
Uri, correct me if I'm wrong.
About what?
So this sort of back up the slide, the fact that you have an order of log n approximation algorithm is saying that if you went back to your balanced bipartite graph and you said, well, it has on the right-hand side independent sets of size n over log to the fourth of n, then you should be able to find something of size n over log to the fifth of n. Is that right? I mean, no.
Sorry, if you.
No, it can't be hard, because if it were hard,
because the way it's stated, it's under the assumption that these deltas are smaller than 1.
right.
It don't state
It
in
doesn't.
case that delta is larger than
If delta is larger than 1,
you don't get an improvement and you stop at 1.
Okay. Okay.
Will we see, I mean, will you give us any idea of the proof so that we
Yeah,
can
I'm just gonna
understand
give the
why
proof.
delta less than 1 comes in? Because, yeah, it looks a little strange.
Why delta less?
Well, you know, why it won't work, why you won't get an improvement for delta bigger. Anyway, well, so you're going to give us a little.
I'm going to give us the proof of reduction. The sketch I'm giving doesn't talk about gamma and gamma prime, but it talks about delta and delta prime.
Good.
So if you give me this graph G, we are going to construct this instance where it's going to have, so let me draw the picture. So we are going to copy log n copies, a constant factor of log n copies, where constant is C. If you want more details, it's related to gamma and gamma prime. But for the moment, you can think of just put log n or a constant factor of log n copies to the right. And we are going to put the edges in between. Now, how we are defining the edges? So these are going to be our sets. These are going to be our elements. So we have P copies here. And we start with the first one, which is H1. H1 initially is our own graph G. So put a copy of G here. And then to go from H1 to H2, you remove every edge with probability 1/2.
So S has n elements, I think.
So this is n vertices. These are also n vertices. This part is just a graph G. Then to go from H1 to H2, you have the same graph, just remove every edge with probability 1/2. And do the same to go from H2 to H3, delete every edge with probability 1/2, and continue until you get to HP. So we have n vertices here, n vertices in each of these copies, and you start with G, and then you reduce the density by a factor of 1/2 when you go down. Now, this is not the whole construction. I'm going to add some edges now. And I define a random graph somewhere else, which has, again, the same size, n vertices and n vertices, and put this random graph on all these copies. It's the same random graph that I defined.
But your HP has a much lower downstate.
It has a much, yeah.
And so presumably this random set that you add is going to have a much bigger effect on HP than on
Yeah.
H1. Yeah.
Yes.
Relative. I mean, right.
Yeah. So what is this random graph? This is just a bipartite graph. Again, as I said, has n vertices on each side, and every edge, the probability of every edge is 1/n to the gamma. So you can, the correct way to look at it is that the expected degree of this random graph is n to the 1 minus gamma. Now I add this random graph to all those hi's that I have. So these blue edges are added to h1, to h2, up to hp. And it's the same graph, so I don't have this experiment once for every graph. It's the same graph that I add on top of all of them. So this is the definition of the construction, going from G to these graphs. So I have two types of edges. One are these random edges that I added, the blue edges. I call them type 1 edges. The other edges were originally from graph G, but they were deleted from H1 up to HP with probability 1/2 each time. So these two type of edges will behave differently for us. Now, how do we prove that? How does the proof of reduction go?
So this is the instance of the
unique coverage problem.
So the left-hand
These are the
side-
elements,
these are
UIs, and these are the sets. So all of them are the elements. We have n log n, roughly a constant factor of n log n elements. Now, first look at the black edges that were originally from G and were deleted with probability 1/2. First, we show that these edges only cover order of n elements from n log n elements. And that's not hard to prove because density of each of these copies is 1/2 of the previous one. So if you have a lot of elements that are unique covered, for example, in U2, then with high probability, all those edges have been deleted in UP, because the chance of surviving all these rounds is very low. And it's also, if a vertex is unique covered here, the chance that it was also unique covered here and survived all these rounds is very small. So this is more or less a proof.
So you're saying that if it's unique,
just look at the type 2 edges. If a vertex is unique covered by black edge, it means that, so what I'm saying is that the probability that the same copy
it was
here.
multiply covered, so with high probability it was multiply
Yeah,
covered.
that's what I'm saying. With high probability, there are a lot of edges connected to that vertex that were removed. So with this, we can just forget about type 2 edges for now, and we look at type 1 edges. Then we show that if we have a large bipartite independent set, and by large I mean of this size on the left and this size on the right, then for each of these copies, we will have a constant fraction of these vertices are unique covered. The reason is that the density of this random graph is proportional to the number of vertices that we have. So a linear number of edges are coming out with respect to the size, and so we expect a linear number of vertices on the right-hand side be unique covered. And since we have log n copies, then we get this many elements unique covered.
Delta. And before it was n log n, and this is...
So we have, in each of these copies, we will have an independent set of size this, and a constant fraction of them unique covered. So how many copies do we have? We have log n, so you get log n times this, which is this many elements.
So which family of sets are you picking to uniquely cover so many elements?
So I'm saying if G has a large bipartite independent set, just look at one bipartite independent set. It appears in all of these. And these random edges that we add are going to cover, are going to uniquely cover this many vertices in just one copy.
So the collection of sets are edges here in this graph?
The collection of sets.
The question is about the definition of edges.
Or the solution. So you're saying that there is a certain number of vertices
on the right which are uniquely covered.
No, I'm saying if you have a bipartite independent set, a large bipartite independent set, suppose that this is a bipartite independent set in that bipartite graph G, then we add these random edges, the blue random edges, they're going to uniquely cover a constant fraction of them. So if your bipartite independent set has size this, you are going to uniquely cover a constant fraction of them. And it's going to happen in all copies because it's the same set. So you get log n times that many elements unique covered here by type 1 edges.
Because we have log n sets.
Yeah, because we have log n copies of p is like something like log n log n.
Okay, but that's still less than what you got at the type 2 edges.
It's actually
Most-
larger. Yeah, because it's delta is smaller than 1. So it's this is
Well, before I
So
had
maybe,
log n.
maybe I'll try to say it a bit. So originally there was this bipartite independent set that we treat the left hand, and then in the reduction, when we reduce it to the unique coverage, we treat the left hand side of the bipartite independent set as the sets, and the right hand side as the items that we need to cover. And then we make these many copies, and in some of the copies we remove some of the edges. And then in addition, we add some new edges to the graph. And in fact, in the case of the yes instance, these new edges are what would give us the good cover. And how would they give us the good cover? We'd select on the left-hand side, in the yes instance, there is a big bipartite independent set in the graph. So we'd select in the left-hand side those vertices, the sets that we'll select will be those vertices from the bipartite independent set that corresponds to this large bipartite independent set to the left-hand side of this bipartite independent set. And then the claim is that they would cover many vertices on the right-hand side. And why is that? And this is using these random edges that we added, this random graph that we call G prime, I think. And why is that? Because the degree of each vertex in this random graph is roughly, we set it to...
it was n over n to the
1 minus gamma,
1 minus
and there are n to the gamma vertices, and these are random edges. So on average, this random this random set of edges covers a constant fraction of the vertices on the right-hand side once.
Uniform.
Each one of them would be covered exactly once. Roughly 1 over e of the vertices would be covered once. And since this set is random, then it's likely to hit this its partner side of the bipartite independent
this
set.
section.
Also 1 over e fraction of it to hit it exactly once. And the point is that the other type of edges that we have don't interfere with it because this was in independence.
So this is the yes case, and for the no case, because we will have a smaller bipartite independence as always, we don't get this. We don't get that many unique covered element by these random edges. So if we have a large bipartite independence set, we get this many unique covered elements by these random edges or blue edges. And if we don't have, then the number of unique covered elements is going to be small. And it's the difference is just exactly the number of copies we have, which is log n times one of these two.
And we said that gamma prime was less than gamma.
Gamma prime is, or delta prime, you mean?
Well, both. I mean,
Uh,
assume you use the same
They go in the
definition.
opposite direction.
They are in the opposite direction.
Oh, they are? Oh, okay.
Gamma prime
I
is less
didn't-
than gamma.
I didn't talk about gamma prime because the gamma prime only comes to play in the number of copies that we have here.
I see, okay. So delta prime is,
Delta prime is smaller. Sorry,
no.
It's larger.
Delta prime is bigger, so the one
Yeah.
minus delta prime is smaller.
Yes.
Good. Okay.
see, even myself get confused sometimes. So So let's see if I can give the sketch of the proof of the first two steps, because the third step is very similar.
All right, so are we already seeing why delta, I think we're already seeing why your delta had to be less than 1, aren't we?
Why delta can't be larger than 1.
Delta were larger than 1, then we have a sub-density of uniquely covered.
Because you always have a cover.
Right.
You can always cover
Right,
linear
so that
cluster.
would be a trivial, that would be
You can always do it.
a trivial statement.
Like
I mean, and you could do better trivially.
Yeah.
you can,
Right.
well, the algorithm is always giving n over
Yeah.
log n at least. There's always
So
a
you could- Right. So you could trivially,
Yeah, but
your algorithm would not be improving the trivial thing
Yeah.
if delta were bigger than 1.
yeah.
Okay.
Because one other way is that the type 2 edges become very, I mean, this becomes irrelevant then to compare to order of n if delta was larger.
Yeah. But also you wouldn't do that, you would just do the trivial.
Yeah. So the first part is easier, and I've already given the idea why it's true. So we are talking about the edges that were coming from originally from the graph, and we just deleted them with probability 1/2. And our claim is that the number of vertices that are unique covered by these type of edges is at most order of n out of n log n vertices that we have. So just consider one particular vertex and all the corresponding copies in these log n copies that we have, and assume that I want to see how many times it can be unique covered by an edge, by a black edge. So if it is unique covered by a black edge in all these copies, then the probability, since it goes down with 1/2 from one copy to the other, the probability that all of them are unique covered by a type 2 edge is 1/2 to the I. It's the probability that the edge survives all these random trials of removing with probability 1/2. So we expect only a few of these vertices be unique covered by one type 2 edge, and if you just do the expectation would be how many vertices we have in each copy, it's n, and the probability of being unique covered I times is 1/2 to the I. So the expected number of vertices that are unique covered by a black edge, or the edge that comes from the original graph, is linear. So that's the first part. Then we want to go for the case that we have large bipartite independent sets. So suppose that our graph, the graph G that we started with, has a large bipartite independent set. We want to show that those random edges, the blue edges that we add, uniquely cover n over a constant fraction of the vertices on the right-hand side of bipartite independence. And Uri already gave the intuition. So just take a balanced bipartite independence set. So suppose that this is the left part, this is the right part. There are this many vertices to the right, there are this many vertices to the left. And note that there is no black edges between them, because this is an independent set. So when you go from one copy to other copy, we are just deleting edges. So there's no edges between them in any of the copies that we have. So the only possible edges are the blue edges. And the probability of an edge in our random graph was 1/n to the gamma. So what's the expected number of vertices out of B prime that are connected to exactly one random edge? It's going to be a constant. And again, if you do the calculation, because the density of the number of edges of the graph G prime is coming out of A, total is n to the 1 minus gamma, so it's a linear number of edges coming out, and it's a uniform random, so we expect them to be distributed among B randomly, so a constant fraction of B prime will be unit covered, and this is the calculation that is required. So that takes care of the yes case, and for the no case, the proof is a bit more complicated, and I don't give it. But we prove this lemma that in the no case, the number of elements that are unique covered by the random edges is at most logarithm of n times the size of the right-hand side in the bipartite independent set. Then we get the desired solution. And the reason is that in any case, type 2 edges are going to be irrelevant because the number of vertices that they unique cover is subsumed by the number of elements that are unique covered by random edges.
Type 2 edges are just coming from the graph G prime.
Yeah, exactly. From the original graph that we deleted.
Right.
So they don't cover many elements uniquely. And yeah, so it's just these random edges that are going to. So the difference that we get between these two cases, this is I don't give the proof of this lemma. So from all these three lemmas, what we get is that if we have a large bipartite independent set, then I've missed the n factor here. The size of the unit coverage should be n times log to the 1 minus delta, and because I've copy and pasted, I have the same mistake here. It's in the no case, it's n times log to the 1 minus delta prime, and the factor, the ratio of these two is logarithm of delta prime minus delta. Now the question is, how do we prove hardness for balanced bipartite independent sets? There's a recent theorem of Cott which shows that that reduces an instance of SAT to a bipartite graph, to a balanced bipartite graph instance, where if the formula is satisfiable, then you have a bipartite independent set of size alpha n on both sides. N is the number of vertices and alpha is a constant. And if phi is not satisfiable, then it doesn't have any beta and bipartite independent set where beta is smaller than alpha. Now, we need a larger gap here, of course. We need the gap here to be polynomial and here to be sub-logarithmic. And also we need the gap to, you see here it goes, there's a difference between the ratio that these two go up. And we can use graph products techniques to amplify this gap to what we need here. And we just take one copy and take a product of it with a suitable constant for the left side and suitable constant for right side. And with this product, we get this hardness, where it is hardness to distinguish between the cases where we have a bipartite independent set of this size and the case that there is no bipartite independent set of this size. And this complexity assumption comes from the main theorem of Cott, which is NP doesn't have sub-exponential running time.
Hodge theorem, there was the same complexity?
Yeah, the same complexity assumption, because the construction is sub-exponential. Now, there are some questions that remain open. The obvious one is to close the gap between the lower and upper bound. It seems that the log n is the correct threshold, but getting the lower bound to log n doesn't seem to be an easy problem. And of course, another thing is that can we get the same hardness or even better under a weaker complexity assumption like NP nothing quasi-polytime, or because sub-exponential it's a bit strong assumption. And with the same reduction that we give, if we think that with the same reduction under this hypothesis, we get a log n hardness. And the hypothesis is that for the balanced bipartite independent set problem, deciding between these two cases is in fact hard, where basically the same delta is now 0 and delta prime is 1. So that's what this hypothesis seems plausible.
So in particular, it could also be log n squared is possible in the denominator there.
Even n to the delta.
It could be a polynomial, but that would be enough for giving the log n hardness for our purpose. I mean, I think this is the weakest one that would imply. Now, this is the last slide. For radio broadcast, we know that there's always a schedule of log square n rounds. And for the case that the diameter of the graph is constant, for example, if we have a bipartite graph and there's one extra node that is connected to one part and has the message. So suppose that this is the source node, which is connected to these nodes, and you have a bipartite graph here. So in the first round, it's going to send all the message to the neighbors. Now it's just a matter of these vertices notifying these vertices of the message that they have received. This is the interesting case that there's a gap between the upper and lower bound. There are such graphs that require log square n rounds. And this was shown by Allen, Barnoy, Lineal, and Plague in 91. And regarding the hardness for such graphs, again, as I said, it is shown that deciding between, by Erkin and Kortsaz, that deciding between these two cases is hard. If this graph has a schedule of with at most log n rounds, or every schedule requires log square rounds. So that would imply a hardness of factor log n, or you can say additive factor log square. So what would be interesting is, can we prove a hardness for the two cases where G has a schedule with constant number of rounds, and where every schedule has omega of log square rounds. So deciding between constant and log square is open. And it's very easy to show that if we get a log square hardness for radio broadcast, that would imply a log n hardness for unit coverage as well. So anything above log n, like log n to the delta hardness for radio broadcasts, implies log n to the delta hardness for unit coverage. So that this seemed to be a more difficult problem. And that's it.